Okay, everybody, as promised, this is the last video on 5.3. And I just wanted to remind you guys that I'm still showing up to our Zoom meetings Monday, Tuesday, Wednesday, and Friday at the same time at 1 p.m. If you have any questions about the lecture, or you just want to let me know how you're doing because you're bored and you want someone to talk to, I can listen and talk to you. Or maybe you want to know how I'm doing, which is, I think I'm going a little crazy. Trying to stay sane. I mean, I have enough work to keep me busy. I still haven't had a chance to binge watch Netflix or anything. Yeah, just managing everything is a little crazy at home because my sleep schedule is a little messed up. So yeah, just want to know that I'm here for you, and always let me know if there's anything I can do for you. If you missed a homework assignment, if you missed a quiz, wouldn't it be a bad idea to email me and see if I can offer you anything? Because I know these times are not normal. And maybe you have an actual good reason of why you missed your homework or why you missed a quiz. And I really want you to pass this class, even considering all these circumstances. I want to see you guys do really well. So please keep me updated or just talk to me about anything, really. We could talk about calculus. We don't have to talk about calculus, whatever you want to talk about. Maybe your other classes are a little rough and you just need someone to vent to. That's fine with me too. Maybe you need to vent to me about this class. That's okay with me too. I can't make this class better if you don't tell me. So I'm always open to that because I want to be the best teacher for you, and I can't. And if you give me feedback on how I can make this better, then I'm open to that. So please keep me updated. And yeah. Okay, so let's get started on net change theorem. Last little bit of 5.3, and that's it for 5.3. And then we only have 5.4, 5.5, and then 7.1. So after this, we have 3 more sections. 3 more sections. And that's it for Calc 1. And then you'll be moving on to Calc 2, which is a great class, by the way. Great class. Actually, I'm going to say all classes are great. All math classes are great. Fun fact. Today I bought my cap and gown for my master's ceremony. And I was like, should I even buy this? Am I even going to get a ceremony? Then I thought about it and I was like, you know what? I'll just walk around my living room. It's fine. Take some pictures with my hair like this. It'll be a graduation to remember for sure. Okay, but enough about nothing. Let's do some calculus. Woohoo! Okay, so net change theorem. So what net change theorem is, it's really just, it's the same thing as what we've been doing, which is finding the area under the curve, but now we're applying these to word problems. So the net change theorem says that an integral of a rate of change is the net change, which is this, which is the integral from a to b of f of capital F prime dx is equal to f of b minus f of a, which is nothing really new. We've already been doing this previously when we're finding the area under the curve, but now why are we calling it something different? This is because now we can use this formula, and we like to call it something different each time, but it's really the same thing. And now we're grabbing this integration formula and the method of finding the area under the curve in order to use it for application problems. So what do I mean by application problems? So we've seen calculus and optimization. We've seen calculus and rates of change, which were all applicable problems. We've also seen applicable problems in velocity problems, like how fast you're going, or displacement in the previous sections. And so this is all that this is doing, is it's a way of using word problems or using applicable problems and applying this formula, this nifty formula that you'll never forget, you'll always use for the rest of your life or the rest of your college life. Or if you want to be a teacher like me, I use it all the time too. So we can apply this to rates of change for all the natural sciences, which most of you are in the natural sciences. So congratulations, you'll be using this. And so we can use it for instance, velocity. I'll just name a few things so that when you see your homework and you see problems that involve velocity or concentration or population growth or displacement, which is, remember, this is just change in position. Or distance traveled, you'll know that you have to use this formula. So here we go. So one way that you can use it, for instance, you can use this many different ways using velocity, concentration, population growth, displacement, distance traveled. But for example, if we wanted to know, for instance, the displacement of a particle, so the net change of a particle over a certain period of time, what we can do is recall that when we're looking at velocity, we can, if we have, for instance, velocity, that tells us the speed of how something's going, right? But if we integrate velocity, we actually get the position function. So if we wanted to know displacement, which is how that particle is moving, or yeah, so if we wanted to know the displacement of the particle, which is telling us a change in position, we can actually integrate velocity in order to find the position between a time 1 or a time 2. So between a certain time, between like time 0 to 0 seconds from 5 seconds, we can figure that out. And so if we integrate this, we'll get the position function, correct? But remember, if we apply this nice dandy formula up here, we'll just do T2 minus S of T1. So what we're doing here is applying that evaluation theorem for our integration, for our definite integrals, and now we're applying them to velocity problems in order to find the change in position over a period of time. Okay, which makes sense. If I go backwards, so if I take the antiderivative of velocity, I will get position. And now I'm just evaluating it at those times to see my change in position over that time. And we'll do an example of that. But before we do that, I want to do kind of an interpretation problem, just so when you see this on your homework, or if you see this on an exam or a quiz, you kind of get a feel for what's going on. So let's do an example. So a honeybee population, I'm gonna do POP for shortcut because I'm lazy, starts with 100 bees and increases at a rate of n prime of t, so the derivative of n bees per week. What does, I'm gonna write 100 plus the definite integral from 0 to 15 of n prime of t dt. So n of t is going to stand for the population of these bees. And so the fact that we know the rate at which it's changing, which is n prime of t per week, so we know that it increases. So it starts with 100 and we know that it increases at this rate. And so they want you to interpret what this means. Okay, so what we'll do here is that if we look at this piece here, right, we want to interpret it. If we say, for example, so let's do a little bullet point here. If we look at the integral from 0 to 15, so I'm just looking at this piece here of n prime of t, right? That's really the same thing as n of 15 minus n of 0 using our net change theorem, which is really no different than our evaluation theorem. So this right here, let's think about what it's representing. If this is representing the rate at which the bees are changing per week, and we know it's increasing, what this is saying, and then we're doing it in weeks, right? This is actually saying that this is the total number of populations after 15 weeks, because we went from 0 to 15. So after 15 weeks, this is what we increased by, right? We don't actually know what it increased by because we don't have the number for that. We don't have a function for n prime of t or n of t. So we actually can't figure that out, but it's just an interpretation problem. So I want you to think a little bit here. And so this represents the increase in the bee population in 15 weeks. And this is 15 weeks because we started at 0 and we went on to 15. We didn't have to start at 0, but for instance, if we went from 5 to 10, then it would be the increase in bees after those 5 weeks between the 5th week mark and the 10th week mark. So that's what it would represent. So this 100 here, if we think about what it represents, is if this is gone, right, that's going to represent the initial population when it started. So if 100 represents the initial population, then 100 plus the definite integral from 0 to 15 of n prime of t dt represents the total population after 15 weeks. Because this part here just represents the increase. So how much did we increase by? But if we add that initial condition of 100 that they gave us in the problem right there, then that is actually representing the entire population after 15 weeks. So that's a very good interpretation of a problem like this. So always for these, think about, okay, what am I dealing with? Am I dealing with velocity, concentration, population growth, displacement? And then think, okay, if I take the if I take the antiderivative of this function, or if I integrate that function, what is that going to give me afterwards? So in this case, the antiderivative velocity is position, just like the derivative of position is velocity. Now think about if this of change of my population, if I take the antiderivative of that, or if I integrate that, what am I going to get? Okay, so let's do one more example. And then after that, you should be set for your homework or a quiz or a test. So you'll be fine. Just watch my videos. It'll be great. Watch my videos, join my Zoom meetings. It's gonna be great. So let's talk about velocity problems because those are fun. I'm a nerd. Okay, a particle moves along a line. So the velocity at time t is, so here we're actually going to give you a function for velocity, t squared minus 2 minus 6, and we'll say meters per second. Okay, so the first thing that I want you to do is to find the displacement. And then I'll talk about part B in just one second. Let's find displacement first, and then we'll worry about part B. Okay, so we'll find the displacement of the particle. And I have to give you a certain amount of time, right? From 1 to 4. So this is referring between 1 and 4 seconds. So you want to know the displacement of the particle between 1 and 4 seconds. So this means that we need to find the change in position of that particle between that 1 and 4 second mark. And so in order to do that, what we need to do is we need to recall that I gave you this, right? But I didn't really need to give you this. If we really thought about what was going on, is that you're given velocity and you want to know how the position is changing. So we know that the antiderivative of velocity is position. So we know we're going to have to use this formula. So if they want to know the change in position between 4 and 1 second, they actually want to know what's the difference in position between s equals 4 and s equals 1. So what they want to know is, how did the position change from s equals 4 and s equals 1, because that's going to tell us that change in position. Okay, so we know that s of 4 minus s of 1 is the same thing as the integral from 1 to 4 of v of t dt. How neat is that? That's a v. That is a v. That's a v. It looks like an r. It's a v. Okay, so v of t dt. And we already know v of t, so it's going to be fine. So we have the integral from 1 to 4. My v is up here. I'm just going to plug that in, which is t squared minus t minus 6 dt. And don't forget dt. This is not dx anymore. This is dt because we're integrating with respect to time. So remember how important I stressed about this here. I'm not going to let this fly if you forget this. And your variable here does have to match your function. Okay? So if we integrate this, this is not too bad. We have a definite integral, so we know we're going to have to evaluate this. It's actually going to be, we just use those power rules. So actually, do me a favor, pause this video, and I want you to integrate this one yourself and see if it matches mine, just so we can get some practice. I just want to make sure we're on the same page. And if you struggle with this, then come to my Zoom meetings, do your homework, do extra practice problems. We have to get good at antiderivatives, okay? So the antiderivative of this is going to be t3 divided by 3 minus t squared divided by 2 minus 6t evaluated at 1 to 4. Okay? And so now from here, my laptop's almost going to die, so I'm going to try to make this example quick, is that now we're going to evaluate, we have to do f of b minus f of a from our net change formula and our evaluation theorem. So we're going to do t to the 4 minus 3 minus, oops, not t to the 4. I'm plugging in the bounds now. So these are my bounds. Is going to equal 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus, now in parentheses, I want to do 1 so that I keep track of all my values and I don't make a mistake when I'm distributing. Okay, so then this is going to be 1 over 3 minus 1/2 minus 6. Now because my laptop's almost going to die and there is a part 3, I'm going to just give you the answer for this right now, but actually what would be a good idea for you to pause it, evaluate this, and see if it matches. So the answer to this is negative 9 over 2, which is the same thing as negative 4.5. Okay, and now you're like, it's negative? It's negative? How is it negative? You're like, how is a position negative? All that's saying is that in this scenario, it's okay for it to be negative. It just means that from your starting point, so let's say you start here, it just means that from your starting point, instead of moving forward, you're actually moving backward negative 4.5. So you're moving to the left 4.5. So it's called a left movement here. So that's okay for a problem like this, to have negative direction. That just means you're moving to the left instead of moving to the right. Okay? And so now what we're going to do is we're going to find the distance traveled. And for this one, you will need a little bit of direction here. So for part B, I want to find the overall distance traveled. So for this, distance traveled involves left movement and right movement. So how far did I move to the left? How far did I move to the right? And I need to add those up. So I could, and as we've seen previously, I did move to the left a little bit, but doesn't mean that I moved to the left the entire time. Did I move to the right first and then I moved to the left? I don't know, right? But overall, there was a movement of negative 0.5. But is that from our starting point, or like what happened? Were we moving right the whole time? So in order to find the overall distance traveled, what you need to do is you have to figure out, when was my velocity larger than 0? And when was my velocity less than 0? So let me give you a little bit of information here. So when our velocity v of t is greater than or equal to 0, this is called a right movement. And then when, and you'll probably guess this one, v of t is less than or equal to 0, this is going to be a left movement. Okay. So we want to find the overall distance. And we know that we can have left movements and we know we can have right movements. So to find the overall distance, we're actually going to take the absolute value of that velocity over that period of time in order to find the exact amount of distance traveled. So we're going to basically find t of 1, the definite integral from t1 to t2 of the absolute value of v of t dt. And this is going to give us the total distance, which makes sense if you think about it. Wow, my writing is getting really sloppy because my laptop's gonna die. And yeah, okay. And so now in order to find the absolute value of v of t and d of t, the first thing we want to do is figure out when our velocity was less than 0 and when our velocity was greater than 0, so that we can break up that absolute value in terms of when we were having a left movement and when we were having a right movement. Just like on one of the examples in the text, when we had an absolute value problem, we separated the area when it went this way to the right for that absolute value, and then here the negative version of that absolute value. Okay. So to find out when v of t was less than 0, what we need to do is, what I would suggest doing is, remember that v of t was equal to t squared minus t minus 6. T squared minus t minus 6. So I'm just going to set it equal to 0 for now, and then I'll explain how you're going to find out when the velocity is less than or when the velocity is greater than 0. So I can factor this. If we factor this, we should get t minus 3 and t plus 2. Yes. And so now to find out when t is less than 0 or greater than 0, what you want to do is we know that we're looking at the time when t is equal to 1 through t is equal to 4. So we're looking at seconds 1 through 4. So our t's domain is 1 through 4. So now we have to think about, okay, when is this, when we plug in 1 through 4, going to cause a negative value? Well, our seconds are always positive, so we're not going to get a negative value here. So we're not going to get a negative value here. So the negative can occur here, because if we plug in 1, 2, 3, or 4 here, it's always going to stay positive. So the negative can actually come from here. And so we need to make sure that this is greater than 0 for the interval 1 to 4. And so if what's going to cause this to be negative is if t really is less than or equal to 3. So v of t is less than or equal to 0 when t is between 1 and 3. Okay, so if I plug in 1 in here, I know I'm going to get a negative value, and this whole term here being negative is going to cause the velocity to move to the left because we're going to get a negative velocity. And 3 is going to cause it to be 0. And remember, we need to check when it's less than or equal to 0 and greater than or equal to 0. So then that means that v of t is positive and greater than 0 when t is between 3 and 4. So now we have bounds so that we can break up that integral. So what we're going to do is we're going to take the absolute value of 1 of 4 of the time 1 through 4 of the absolute value of v of t, that's an absolute value, dt, and we have to separate it from time 1 of 3, and I'm going to leave a blank here, dt, plus 3 to 4, and then I'm going to leave a blank there, dt. And so what's going to go in here is that negative version of the absolute value, because remember that v of t is our function up here. And so this is going to be negative t squared minus t minus 6. And this is just going to be that original function. Okay. So then we're going to get the integral from 1 to 3 minus t squared plus t plus 6 dt plus the integral of 3 to 4 of t squared minus t minus 6 dt. So go ahead and pause this video, integrate both of them, and hopefully your answer matches mine. I'm going to move a little bit quickly here just because my laptop's going to die. I have 7% and we're going to make it. Okay, so if I integrate this, I'm going to get 1 over 3 t cubed plus t squared over 2 plus 6t. From 1 to 3, and then here this is going to be 1 over 3 t cubed minus t squared over 2 minus 6t from 3 to 4. And so now what you need to do is you're going to plug in these bounds into here minus the bound of 1 and do it for each side. So this is really good practice of you plugging in the bounds to find that net change. And so if you plug that in, you should get the answer 61 over 3, which is approximately 10.17. Remember, we were talking about meters here, so the total distance traveled is 10.17 meters. Okay, so not too bad. It's basically everything we've been doing in this section, but now we're just adding word problems to it. So it's applicable and it's fun. Yeah, that's it for 5.3. We're not on 5.4 yet. Crazy. So that's it for 5.3. I'll see you for 5.4, or I'll see you in my Zoom meetings, hopefully. Yeah. I hope you guys are staying home, staying safe, and please let me know if you need anything.